Yes. Okay. Finally, I got the answer. Okay. So now we will be talking about the chemical oxygen demand. Is anybody recording, or I record from my PC? Is anybody recording, or I record? If you want to talk, you can unmute. You can unmute. You can unmute your mic if you want to talk. So, is anybody recording? Okay, so I will record. Okay. So, oh, go, you're recording. Go. Okay. Okay. So please do the recording and we will move forward. All right. So let's. Okay. Just to revise what we have discussed last class. Last class, we discussed the characteristics, the physical characteristics of wastewater. It was temperature, pH. The most important is the suspended solid. And we knew the difference between suspended solids and dissolved solids, and how can we calculate or measure the concentration of the volatile solids, okay, whether it is suspended or dissolved, right? And today I will send you also assignments and the questions for you to practice. And then we move to BOD, and we discuss many things about BOD and how to calculate the BOD, how to estimate the L node, how to estimate the K, reaction rate. Okay, and today we will start talking about COD. Okay, now COD is something more general. I mean, more extensive than BOD. Okay, so COD basically is the chemical organic is the chemical oxygen demand, which means that it's the oxygen needed to oxidize the organic compound, but chemically, not biologically. Okay, so the BOD we estimate the quantity of oxygen that is consumed by bacteria. Okay, so it is a biological process, but in the COD, it's a chemical process, right? It's a chemical process. So it is the quantity of oxygen needed to oxidize, chemically oxidize the organic compound. And here, when we oxidize chemically, we cannot differentiate between biodegradable and non-biodegradable. So that's why COD join together all the organic compound, biodegradable plus non-biodegradable, okay, in the sample. So all the organic compound will be converted to carbon dioxide and water, okay? So here you can see this figure shows that organic compound is the general one and biodegradable is only a portion of it. COD measure all the big circle, which is the organic compound, okay? Right? So here, this is commonly used to define the strength of industrial wastewaters. Why commonly for industrial wastewaters? Because the organic compounds are mostly non-biodegradable. In industrial wastewater, organic compounds are mostly or majorly is non-biodegradable in industrial wastewater. On the other hand, the domestic wastewater, most of the organic compound is biodegradable. Okay, so that's why it's more worthy and more sense to use COD for industrial wastewaters. Although we use COD for both, we can use COD for both. Okay, so we can measure COD for domestic wastewater, for industrial wastewater, for landfill leachate, for any kind of wastewater, we can use the COD. Okay, but mostly we focus For COD, we concentrate on COD in industrial waste waters. Okay. So how is the test procedure? Actually, the test procedure, there is a conventional test, but nowadays there is a modified test or ready-made test, okay, which we just use one reagent, one chemical reagent, and we add the wastewater to it. So this chemical reagent will oxidize the wastewater, okay, will oxidize the organic compound in the wastewater and convert it to CO2 plus H2O. Then we can measure how much oxidized. Okay, this has to be done in the lab, so it's difficult to just to talk about it. So I will leave this part of the of the of the slides. And I will not go in details, but you have to know that the test procedure or the basic concept here is that the organic matter is oxidized chemically. As you can see, this is a chemical equation. There's no bacteria, there's no microorganisms, of course. So organic matter plus an oxidant, chemical oxidant. Here is the dichromate. Okay, is the dichromate oxidant. Okay, and that will be all converted to CO2 plus H2O. So in the conventional method, we used to measure how much radical of the chromate, okay, how much radical chromate is produced. So that will indicate how much organic matter was, or how much organic matter has been decomposed, okay, or has been oxidized. All right. So this is the procedure, and this is the formula, okay, the equation. So either you can measure it in the lab or you can use this formula if you know the concentrations, the normality of the iron of this chemical compound, okay, because this chemical compound is used is used in the testing procedure. So never mind. I will pass through this one because it's not really important. I think it's only one equation. It's a direct equation, so nothing to do with it. Okay, and normally we use COD to measure, or normally we measure COD in the lab, not in the not by equations. Okay, this is a just direct example. You can have it. Results of COD test for raw wastewater, 50 ml are given. Okay, volumes of the ferric ammonium sulfate. FAS is the ferric ammonium sulfate. Ferric ammonium sulfate. So the volume used for blank and the samples are these are the volumes. Okay, so this is ferric ammonium sulfate. These are the volume used, okay, for blank and for the sample, which means that we add this solution to a blank sample. Blank, which means it's not wastewater, is clean water. Okay. Then we bring the wastewater, same volume, and we add to it 12.88 ml. Okay. The normality of the ferric ammonium sulfate was 0.242. Okay. You can calculate the COD concentration for the sample. Okay. So how much the concentration? Just directly substitute in this equation, and then it's all done. Okay, it's a direct equation. I don't want to go in detail because, as I said, nothing to do with it. Okay, so this is the simplified COD analysis, and that's actually what we do in the lab. So we don't go for the conventional one. We use the simplified one. Okay, so the simplified one is simply you have this reagent. You see the light yellow color, the light yellow reagent here. Okay. When we add the wastewater to it, it will convert to like greenish. Sorry. It will be converted to a greenish color. Okay, that means an oxidation process is taking place. And then we heat it for 2 hours. Okay, heating for 2 hours. Then we move it out of the heater. So this is the heater. We move it out from the heater, leave it aside to cool down. Then we put it in this equipment. This equipment is called the DR, DR 5000, DR 6000. It depends on the version. But this one is DR. DR, this is the spectrophotometry. So this is all is done in the lab actually. So that's why we cannot. It's difficult to describe it here. It will take a long time and we not be able to understand it very well. But I will post a video for you. Uh, this is all what we can do now. We post a video to show the process in the lab, how it is done in the lab. Hopefully, if study in the university was able to back normally, we can go to the lab and see what is going on. Okay, so now this is one of the important things we have to understand. What is the relationship between COD and BOD, right? As we said, COD measures the concentration of all organic matter, okay, biodegradable and non-biodegradable. But for BOD, it measures only the biodegradable, okay. So in that case, we can anticipate or we can suppose or we can propose that COD is larger than BOD because COD is measuring something more than BOD. Okay, so it includes the BOD. So in that case, always COD is bigger than BOD, which means that COD is bigger or equals the L node. So you know the L node, right? L node is the what? L node is the ultimate BOD, correct? Because BOD5 is less than the L0. The maximum biodegradable, the maximum amount of the ultimate amount of BOD is L node, correct? So if we can sense the L node means what? Actually, L node means that if we suppose that all the biodegradable organic will be decomposed by bacteria, 100% decomposed, we will reach the L node. So this is the ultimate. BOD5 does not reach the L node. It reaches like 90% of the L node. I don't know how, maybe 80% of L node. Okay, it's a portion of L node. But L node practically cannot be reached, but theoretically it means that the whole biodegradable organic matter is decomposed. Okay, if we are able to decompose the whole organic matter, okay, in the um, carbonaceous POD, okay, so that means that the whole biodegradable organic matter has been decomposed, okay. So that's what we mean by BOD, by L naught. So COD is at least it will equal the L naught, or maybe it will be higher than L naught, okay. And in most cases, it is higher than L naught. It is higher than L naught. All right. If we measure for a sample of wastewater, if we found that COD over BOD is almost equal to, which means that like if COD is 100, so BOD is 50. Okay, if COD is 200 and BOD was 100, so that means the ratio is 2. Okay, so that means there is high concentration of biodegradable organic. Okay, there is high concentration of biodegradable organic. If the ratio was like okay from 2 1.5, that means there is high biodegradable organic. So this is the minimum. Okay, I can write here that this is 2 or less. Okay, 2 or less. So if the ratio was 2 or less, that means there is high portion of biodegradable organic. Okay. Now, if the COD was much higher than BOD, like 1 to 10, like 10 times or 5 times, okay? So that means the majority is non-biodegradable organic, okay? The majority is non-biodegradable organic matter. Like if the BOD is only like 20 and COD is 100 something, so that means most of the organic matter is non-biodegradable organic. Okay, so the ratio of COD over BOD is approximately 2. That is normally before wastewater treatment. Okay, and after treatment, the ratio should increase. Okay, after treatment, the ratio should increase. Why? Why the ratio will increase after treatment? Can you guess why? If you want to open the mic, you can also. Yeah, let me see who is active. Hmm. Can you explain why? Concentration decrease. Concentration of what? Concentration. Concentration of what? I think I have to put the my word in silent. Okay. After after treatment, the ratio will increase, which means that if COD over BOD before treatment was like 2, okay, after treatment the ratio will increase. It will be 3, 4, 5, maybe it will be reach 10. Okay, that means the BOD is less, getting less because you are treating wastewater. Correct. COD over BOD was 2. Okay, it was 2 before treatment. Right. Now, after treatment, what does it mean? What do you mean by after treatment? After treatment, it means that we are removing the biodegradable, we are processing the biodegradable organic through the biological treatment methods and so on. Okay, so that means a good portion of the biodegradable organics was was decomposed by the bacteria. Okay, that's actually what happened in the treatment. So the BOD will become less. If the BOD initially was 100, it will become like 20, 10. Okay. On the other hand, COD will become less, but not too much less. If it is 200, it will decrease only maybe to 100. Okay, because there is a portion of non-biodegradable organic still not treated. Okay, so this is after the organic, and this is after the biological treatment. Okay, just to make it more precise. So after biological treatment, the ratio will increase. Okay, that's one. All right. Um, so if COD over BOD equals 1, what does that mean? If COD over BOD equals 1, what does it mean? You can open the mic to speak or you can write in the chat. COD over BOD equals 1. COD and BOD have the same value. Correct? Yeah. COD equals BOD. No. But what does it mean if COD equals BOD? That's the main question. What does it mean that COD equals BOD? Yeah, anybody can guess. If COD equals BOD, what does it mean? Have non-biodegradable organic. Okay. COD only have biodegradable organic. Okay. Hmm. Okay. Okay, that's right. That means that means that all the organics are biodegradable. Correct. So all of you have, Jing and also Kong Zi Bin. Those the two person that answer. Correct. So the answer is all the organic content is biodegradable. All of it is biodegradable. For example, if BOD is 50 and COD also 50, so that means all is biodegradable. There's no non-biodegradable. If BOD is 100, and also we found that COD is also 100, so that means the whole organic compounds is is biodegradable. Okay, is biodegradable. So this is what does it mean. But of course, this is an ideal case. It's not it's not practical, but at least we understand the concept. Okay. Okay, so here we have COD versus BOD. COD possibly or mostly is the process performance testing, which means that we can run it every day because the test takes only 2 hours to 3 hours. Okay, so it's a process performance testing, while BOD is a compliance testing. Compliance means that we want to see if this method is compliant or not, is suitable or not. So we can run BOD. Okay, so BOD because it takes 5 days, we cannot monitor the day by day treatment of wastewater using BOD. It's difficult using BOD. Okay, so we have to use COD because if I put the sample today, I will have the answer after I have the final result after 5 days. So after 5 days, after only 5 days, I will see if the treatment was okay or not. Okay. COD over BOD cannot be less than 1. If it is less than 1, if it is less than 1, COD over BOD cannot be less than 1. Why? Because it doesn't make sense that because COD is the general one. Okay, so BOD is a portion. So the portion cannot be bigger than the boundary. Okay, so it doesn't make sense. Uh, okay, so mostly the COD is higher than BOD, right? COD is higher than BOD. But in ideal case, I'm talking about the ideal case, the COD is equal BOD. That means all the compounds are biodegradable. But this is only an ideal case. Okay. So let's move. Now this is the chemical characteristics of wastewater. We continue talking about the inorganic compounds. So all our talking in BOD and COD is about the organic compounds. Okay, organic compounds. We know the organic compounds is the carbon and hydrogen. Okay, bonded together with nitrogen and other elements, right? But the inorganic compounds is a definition when they are placed in water, they will be changed to electrically charged atoms. Okay, they will be dissociated into electrically charged atoms. Okay, those are, we call it the ions. Okay, so we have negative ions and positive ions. Okay, so all atoms are linked in ionic bonds, and here we have the ionic bonds. It's different from the organic compound bonds. Okay, so for example, we have the sodium chloride, we have the calcium hydroxide, okay, aluminum chloride, and so on. So this is all the inorganic compounds. Okay. So what are the sources of inorganic compounds? So mostly they are covering the nutrients. Okay. Nutrients. When we talk about nutrients, we are talking about phosphorus and nitrogen. Okay. Phosphorus and nitrogen. So those we call them nutrients. So let me write here. Okay, nitrogen and phosphorus. Okay, so nitrogen and phosphorus, those are called the nutrients. Okay, we have the alkalinity, the chlorides, the sulfur, all these inorganic pollutants. Those are called uh, those are the sources of inorganic compounds. All right. What are the effects of increasing nitrogen and phosphorus in the water bodies? Okay, so if nitrogen and phosphorus are discharged in water bodies without being treated, if they are just disposed to the river or disposed to the lakes without being treated. What does it mean? That means what? That means there is an excessive algae breeding. You remember in chapter 2 that when we talk about the algae, so the algae mainly depends on the presence of nutrients. So they feed on the byproducts of bacteria, okay, like the nitrate, the sulfate, okay, the phosphate. So all of these, the presence of all of these nutrients will increase the breeding and the growth of algae. All right. So that means they will cause the thing that we call it the eutrophication. Eutrophication means that is the increase of nitrogen and phosphate, or it is caused by the increase of nitrogen and phosphate in the water bodies. Okay, what will happen if nitrogen and phosphate increase in the water bodies? More algae will grow up, and this will result what? So let me just write it here. Just instead of talking, I think I can write something here. Okay, increasing nitrogen and phosphate means that okay, it will lead to what? Okay, lead to increase algae growth. Okay, and when algae grow in huge amounts, that will cause what? That will cause the prevent sunlight penetration. Correct. Okay. Why? When there is an algal blooms on the surface of water, okay, so it will penetrate the sunlight from entering to the water body to reach the aquatic life. Okay, and also it will make depletion of oxygen in water. Okay, so those are the two main effects: prevent sunlight penetration and depletion of oxygen in water. And you can imagine if those two things happen, what will be the result? The result, it will be die. It will be die of the aquatic life, you can say. Okay, so this is the main effect that will happen from the eutrophication. Okay, so that is called by the eutrophication. All right. Okay. So eutrophication, when the water body, again, eutrophication, when the water body, like a river or lake or whatever, when it becomes overly enrichment with minerals and nutrients such as nitrogen and phosphate, okay, that will encourage more and excessive growth of algae. So this process will result in oxygen depletion and prevent the sunlight penetration to the water body, okay, and eventually will cause die off of the Atlantic. Okay, all right, let's move on. So nitrogen presence in wastewater, it can present as organic nitrogen, or it can present also as organic nitrogen, ammoniacal nitrogen, nitrite, and nitrate. Okay, organic nitrogen, it can be the organic compound, okay, included in the organic matrix. Ammoniacal nitrogen is the NH4, okay. The nitrite and nitrate, of course, is the right here is the NO2 nitrite, and nitrate is the NO3. Okay, so we have the nitrite and the nitrate. Okay, now if there is a high concentration of ammonia in the wastewater, that means it is fresh. What does it mean it's fresh? It's not an old wastewater. I mean, it's not treated. Okay, it's not treated because by time, if you leave the wastewater, by time this ammonia in the wastewater, it will convert to ammonia gas. It will convert to ammonia gas. Okay, but if the ammonia is dissolved in wastewater in high concentrations, that means this wastewater is still fresh, still newly produced. Okay. All right. So under aerobic conditions, the ammonia will be oxidized to nitrite and then to nitrate. Okay. So the ammonia will be oxidized to nitrite, then to nitrate. This is under the aerobic condition. And that process, we call it the nitrification. Nitrification, okay? So what is the process of nitrification? It's actually a biological oxidation. It is a biological, let me write it here because I feel that when I write, it would be more better for me. So it is a biological, this is nitrification, okay? This is nitrification, biological oxidation of ammonia to nitrite. Okay, then uh, then oxidation of nitrite to nitrate. Okay, so the biological oxidation of ammonia to nitrite, then to nitrate. Okay, so this transformation from nitrite, from ammonia to nitrite, and then from nitrite to nitrate, this transformation is called biological oxidation is called the nitrification. Okay, so here is the nitrification. This is nitrification. Okay, so this is nitrification. It's biological oxidation of ammonia to nitrite and then to nitrate. Okay, let's move on. Um, this was the last slide. Oh, okay. So, luckily, we have finished chapter 3 now, finally. Uh, okay, so we have finished chapter 3, and so we just make a brief of chapter 3. So, chapter 3, we have talk about the types, the characteristics of wastewater. Okay, types of wastewater, we have domestic, and we have industrial wastewater. Characteristics of wastewater, we have physical, biological, and chemical. Okay, so the physical characteristics of wastewater, we talk about temperature, the pH, the odor, and the most important is the suspended solids. Suspended solids. Okay, suspended solids. We talk about uh, dissolved and suspended. Okay, total solid, dissolved and suspended. And we have also the volatile and non-volatile. Okay, and how to measure each of them. And then we move to the biological characteristics, which is the BOD and COD. Okay, the BOD, basically the BOD. Okay, and we know how to measure the BOD. What is the BOD ultimate? What is the carbonaceous and nitrogenous BOD? All of these um, uh, combinations. Okay, and we move to COD, and we know what is the relationship between COD and BOD. Then we have a brief idea about nitrification, because this is related to the chemical characteristics of wastewater, the presence of inorganic compounds. Okay, and nitrogen, one of the inorganic compounds, and then we move to the eutrophication, and we have a brief idea about eutrophication and what causes the eutrophication. Okay, so this is chapter 3. If you have any question, let me know. Let me know until we prepare for chapter 4. Okay, because before we move to chapter 4, we need to discuss something related to the discharge of wastewater. Can you see the screen? Can you see the new screen? Okay, good. Okay, so the new screen here, we're just talking about this. This is a brief one. This is a brief one. After this, we will have a break. Okay. So, what is the discharge standards of waste water? Okay, and a brief idea about the Sewerage Act. Now we know that um, after treatment, or there is a governing regulation of treatment. Okay, so this regulation controls the treatment of wastewater. Okay, controls the quality of treated wastewater and to how or to what level it should be reduced. For example, if we want to discharge the wastewater after treatment, if we want to discharge it to the river, so how much the BOD has to be, maximum how much the COD has to be, how much is suspended solids, those are the pollutant parameters. Okay, for each parameter, we have to reduce it to some certain level, before discharging to the sea or discharging to the river or to the lake or wherever we want to discharge. Okay. Now, what is the wastewater standards? Okay, the wastewater quality standards, it follows the environmental quality regulations in 2009, and this is a national regulation. I mean, in Malaysia, okay, because each country has its own standard. Each country has its own standards for wastewater quality, like like any other product. Okay, if we are talking about the drinking water, Okay, so there is a certain standard for drinking water. Okay, it has to be like the purity, the color, and the pH, and many other parameters has to be fulfilled by the producer or by the manufacturer. Okay, and same goes to the wastewater treatment. So this is a set of standards for new sewage treatment plants and also for the existing sewage treatment plants. This was approved finally in 1999 and then edited in 2009. Okay, now for the standards, we have two categories or we have two classes, let me say. We have class A and class B. We have standard A and standard B. Okay? If you go to the market and you want to buy a shirt and you want to buy a coat or you want to buy shoes, for example. So you have shoes class A, you have shoes class B. You have shirts class A, which is high price. You have shirt class B, which is lower price. Okay? What is the difference between those two things? Equality. Equality, yes, correct. Equality is the main difference. Okay? So same goes to the wastewater. Same goes to the wastewater, which means that for standard A, it means that the quality of this treatment is higher than the quality of treatment of standard B. But sometimes we allow standard B, and sometimes we strictly have to follow standard A. So now we will know why standard B and why standard A. Okay. So this is the hierarchy of the act. So the act was approved in 1974. Okay, and then the environmental quality regulation in 2009 came. Under this regulation, we have the regulation 7, and it gives the acceptable conditions of sewage discharge standards A and B. Okay, so these are the parameters. We have temperature, the pH, the BOD, the COD, suspended solids. We have the oil and grease. Okay, we have the ammonium and nitrogen. If the water will be discharged to the water body, and like a lake, for example, and ammonium and nitrogen if the wastewater will be discharged to the river. Okay, same goes to the nitrate. Nitrate if for discharge in the river, and nitrate if this will be discharged to the water body. Same goes to the phosphorus. Okay, and you can see in standard A and standard B, there is a difference. Okay, there's a difference between standard A and standard B. Look at BOD, for example. Okay, in standard A, it's only 20. Okay, it's 20, but in standard B, it can go up to 50. So that means the quality of standard A is higher. The quality is higher, okay, because we are reducing the BOD. Okay, when we say that BOD is 50 and BOD 20, so the BOD 50 is more polluted. Okay, right? And same goes to the COD. COD, the standard A is not more than 120. But for standard B, it can go up to 200 because it is lower quality of treatment. Okay, suspended solids same 50, 100. Okay, you can see the oil and grease, the ammonia, nitrogen, and all the parameters will be different. Okay, if standard A and standard B, some parameters will be different between the two standards. Okay, all right. So, and these are the parameters for the existing sewage treatment. Okay, when they approve the regulation, they have already existed treatment plants. So these standards has to be followed by the existing treatment plants. Okay. Now we will see when we can use standard A and when we can use standard B. It is noted here, but I will explain it in the following example much clearly. Okay. And this is the standards of wastewater for each treatment unit. Okay, we have the septic tank, the imhoff tank, the aerated lagoon, oxidation ponds. These are units inside the treatment plants. Okay, so for each unit, how much the treatment or what is the standard of discharge treatment for each unit, not for the whole treatment, but also for the each unit. Okay, this is only for your information. You don't have to memorize all the numbers, but at least you know the differences between A and B and why we follow these regulations. Okay. All right. Now this is a practical example, okay, or a real example. Here we have UTM. As you can see, we have UTM, and here is the McDonald's. You know the Petronas and McDonald's, very near to the gate here, and here we have the Padangkawad. Uh, okay. Here we have a wastewater treatment plant. You can see the four rectangles. Okay, four black rectangles. Those are here we have a wastewater treatment plant, a small wastewater treatment plant inside UTM. Okay, can you see the the cursor? Can you see the cursor, the mouse? Okay, okay. And also we have the cursor is clear to you. You can see the cursor moving. Can you see the cursor moving? Okay, all right. Just raise your thumb. Okay. So we have the treatment. We have the wastewater treatment plant here. Okay, and also we have the McDonald's. Here we have the highway going to the JP. Okay, here we have Sumbu Ajoho. So here is the water collection. I mean water distribution plant. From here they collect the water from the river, and we have this is a river. This line is a river coming from up to down. Okay, this is a river that obtain water from it. Okay, now this is a more close or zooming view. You can see this is the treatment plant, and this is the river. Okay, the river is running over here. Okay, now from the treatment plant, there is a line. You can see this line. There is a line of discharging wastewater to the river. Okay, this line is discharging the wastewater to the river, crossing the road and then discharging the water to the river. And here we have an intake point. We have water intake point. Water intake point, which means that from this plant collect water from the river at this point. And we have at this wastewater discharge point here. Okay, but which one is before? Which one comes before? Of course, the water intake point comes before because the river is coming from up to down. Okay, all right. So these are the lines of water and wastewater moving. So this is the line of wastewater moving, and this is the line of the arrows showing the direction of water, and this is the wastewater. All right. So here also the UTM shows that this is the UTM STP. STP means sewage treatment plant. Okay, and here the intake point. Here the intake point of water. Now, if the wastewater is discharged after the intake point, okay, so do you expect that we can use standard A or standard B? In this case, that you can see now, can we follow standard A or standard B of discharging waste water? Standard A or standard B? What do you think? Here we have to follow standard A, or we can follow standard B as well. Standard A and B. Yeah, we can follow both of them, I know. But which one here is preferred? Standard A, based on their location. So based on their location, well, standard A is more better, okay, but standard A sometimes it costs a lot. I mean, the cost is higher. When we want to achieve standard A, the cost is higher. So here, can we use standard B or not? That's the main question. Can we use standard B or not? Can we follow standard B or not? Yes, 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 of course. Yes, we can follow standard B. From UTM STP, yes, we can follow standard B. Why? Because the intake is coming before the sewage treatment discharge, correct? So we are collecting water before mixing with any kind of wastewater, any kind of polluted wastewater. So we can safely dispose standard B because there is no any intake point coming here, coming in this area, in this line. Okay, there is no any intake water intake points. All right. So in that case, we can follow standard B. Okay. Now this is a more close photo. So this is the Sumber I Johor, here the intake point, here the UTM STP discharge. Okay, so this is standard B. Now what about other discharge points? Okay, you see there is other discharge locations. So what about those others? Has to follow standard A or has to follow standard B? Of course, the one just before the intake point has to follow what? Has to follow standard A. Correct. Has to follow standard A. Okay. So this one standard B, okay, but this one has to be standard A. Same the others. Okay. All the others here has to be standard A. So those we call them, those we call the upstream, and here we call it the downstream. Okay. So the one before the intake point is called the upstream. The one after the intake point calls the downstream. So in the upstream, we can use or we can follow, we have to follow standard A. Okay, but in the downstream, we can follow standard B. Right? So here we will write this one is called the upstream. Okay, and here is the downstream. Okay, and this is the intake point is over here. Okay. Okay. Now, Nabila says, be any discharge from STP below intake point. Okay. A is any discharge before intake point. B is for any discharge from STP below the intake point, which means after the intake point. Correct. Yes. So that describe or let's make it briefly. B, standard B is after intake point, standard A is before intake point. Okay, so that's right. Okay, so if you understand this example, you can differentiate between standard A and standard B, and when we should use both of them. So same goes to the drinking water quality standards. This is also basis as guideline for drinking water quality to be achieved by the water treatment plant operator. And all these quality standards, basically they are prepared by the Ministry of Health based on the World Health Organization standard. WHO is the World Health Organization standard. Okay. These are the drinking water quality standards. Okay, is somehow different from the wastewater quality standard. Why? because this is drinking. Drinking means that it will be in contact with humans. Okay, we might put it in our mouth, we might wash our face, might take shower. Okay, so that's the drinking water quality. So the quality has to be much better than standard air, much better than standard air. Total coliform, there has to be no total coliform. The coliform means the organisms, okay, the microorganisms, means the bacteria. Okay, there has to be no bacteria. We cannot use water which is contaminated by bacteria. That is totally prohibited. Okay, the E. coli same, Escherichia coli, the fecal streptococci same. It has to be absent. It has to be definitely absent. Okay, turbidity, color, iron, hardness, all is very low amounts in the drinking water quality because this is in contact, direct contact with the humans, so it has to be in high safety for humans. All right, so we have finished now chapter 3 and the attachment of chapter 3. So if you have any questions, just let me know. And now we move to give you a break. Give you a break for 10 minutes and we come back again to start in chapter 4, one of the easiest and one of the most interesting chapters in our course. Okay, so we see you after 10 minutes. Don't go away. See you. Okay. Now, in the previous chapters, our discussion was only about the characteristics of wastewater. Now, if we want to go for a design of a wastewater treatment plant, that means we have to know the characteristic of wastewater and also the quantity of wastewater, how much quantity, how much volume, how much flow of wastewater is coming or is to be generated. Okay, and the production of wastewater depends mainly on what? Depends mainly on the water demand. The water demand, the water usage. How much water, the more we use water, the more we produce wastewater. Because wastewater is produced from using water. Okay? So the more we use water, the more we produce wastewater. So this is logic. Okay? So the water consumption rate is different from place to place, it's different from country to country, it's different from city to city, maybe. Okay, so that these are some numbers of estimated water consumption rates. Okay, for example, the city more than 10,000 person, the water consumption rate is 230 up to 300 liter per person per day. Okay, one might ask, if is it logic that one person consumes 200 liters per day? Yes, because that includes everything. It includes your personal use, includes the cooking, includes the cleaning, includes the dishwashing, includes the laundry, includes everything. So that is okay. Okay. So it's not only a house, it's a group of, it's a community. It's a usage of one of a whole community. Okay. So that is also logic. That makes it logic. The suburban areas, it's less. For heavy industry and light industry, there is a difference between the usage. And normally we measure it in terms of hectare, liter per hectare per day. Okay, right. So the water demand has so many categories. These are the main categories of water demand. We have the domestic, it means the houses, the schools, the hospitals, all human use. Okay, and public use, which is the open use, the public parks, maybe the masjid, maybe the temples. Okay, so water use there is public because anyone can use free. Okay, there's no charge for it. And also we have the fire demand. You know the the hydrants located in the street. This has a special water demand, especially for it. And also we have the commercial and industrial uh, use. Okay, in the shopping mall, the factories, manufacturers, and the restaurants. All this is considered as commercial and industrial. All right. So the more demand, the more wastewater production. Okay. So here we comes to a point that wastewater quantity varies also hourly, daily, and weekly. Okay. So we expect that at night wastewater generation is less than the daytime, correct? Because at daytime, all people are active, they are waking, they use water, they clean their cars, they make laundry, they take shower, they do all the activities that consume water. But in the night, at night, most people are sleeping at night, so there is no such high generation of wastewater. Okay, so during the day, the wastewater demand is fluctuating. Generation is fluctuating. Okay, high and low. So that makes at certain time there is a peak flow. There is a peak flow of wastewater at certain time. Okay, all right. So okay, here comes some definitions. Some definitions. What is the sewage? What is the sewer? What is the sewage treatment plant? What is the sewage system? Okay. So the sewage is any liquid, the liquid discharge. Normally we use it for domestic source. Sewer is the pipes, the pipelines that carry the wastewater. Okay. The sewage treatment plant is the site designed to treat and to receive the wastewater. And finally, the sewage system is the whole system, starting from the collection point and ending with the discharge point. This is all we call sewage system. Okay. Okay. Now, in order to be able to calculate or to estimate how much wastewater quantity we have for the whole community, including houses, including hospitals, including hotels, including schools, including mosque, including temple, including all the buildings and premises and the type of usage that use water daily. Okay, so how are we going to add hotel use to a hospital use to a house usage of water? It's not possible to add them just we estimate the numbers. No, we have to follow a reference. We have to follow a reference. Now remember the chemistry. In the chemistry, when we want to, if you have a solution, okay, and this solution contains sodium, contains potassium, calcium, sulfate, phosphate, carbonate, so many compounds. And you want to measure the concentration, the molarity, okay? How much concentration we have. So can you add simply, can you simply say, okay, we want to add sodium, let me write here. We want to add like, okay, sodium plus potassium plus calcium plus phosphate, okay, equals like 200. No, this is correct. This is totally wrong. Okay, you have to convert sodium to the molar weight, and then convert the calcium to the molar weight, convert the potassium to molar weight. All the elements have to be converted to molar weight. This is something equivalent, okay? The molar weight is something equivalent, like 100 potassium equivalent to blah blah blah. 100 calcium equivalent to da da da. Okay, so it's like an equivalent. It's like a reference you have to follow. You have to refer to it. Okay. Same goes to the water demand or wastewater generation. Right? We have hotels, we have hospitals, we have schools, we have houses. Okay. So what is the equivalent? The equivalent is the population. Is the population. So that comes to the reference or to a term or a definition, which is the PE, population equivalent. Okay, so the population equivalent it's an equivalent, okay, in terms of fixed population or transient. Fixed population or transient, which means that if the population is during the whole day, 24 hours, or transient, it means that it's changing by time or changing by day. It's not spending the whole day in this premise, okay, for any activity. What is the population equivalent? For example, for one house, what is the population equivalent? For one hospital, how can we convert it to population use? For a hotel, how can we convert it to population use? Okay, so for each type of premise, we have a number of PE. Then we can calculate the total PEs for all the premises. Okay, if you have any question regarding this, just please let me know. Okay, please write in the chat because I can't see all of you now, right? Okay, now, so what is the PE? So as I said, for each type of premise, it has a number of PE. Okay, for example, for houses, 5 PE per unit. We have 5 PE per one unit, one house. Whether it is a double story, whether it is a detached, for one house, we have 5 PE. Okay, it's like if we say for one house, the average is 5 people living there. Okay, one house might be 3 and the other 7 and the other 10. So the average is 5. Okay, so this is the average. It means that the average of people using water inside the house. Okay, so it is 5 PE per unit. If apartments, yes, we calculate one apartment, 1 unit. One apartment, 1 unit. One house, 1 unit. Double story house, 1 unit. Okay, that's all is 1 unit. Okay, for the shopping mall, we calculate the PE based on people? No, they're not. Why? Because people are coming in and out. You go to the shopping mall 1 hour, 2 hours, and then you go out. You might use water, you might don't use water. Okay? But the more big or the bigger the shopping mall, the more usage of water. There is cleaning, there is cooking in restaurants, there is toilets, there is right. So that means we have to calculate the PE of the shopping mall or of the commercial areas, let me say, commercial buildings using that area. Using that area. Okay? If it is one story with an area of 1,000 meter square. So for each 100, you have 3. So 3 times 1,000 over 100, which is 30. Okay? If the area is 3,000, so 3 times 3,000 over 100, okay, which is 90. If we have double story, so you have to times 2. If you have 3 stories, it has to be times 3. Okay, for each story, it is considered as a new commercial area. It is unlike the houses. Okay, so this is one of the tricks you have to follow. So in that case, we can add together the water usage in the commercial building, together with the water usage in the houses, together with the water usage of the schools. We have 0.2 PE per student if it is a day school, and if it is a residential school, so it is 1 per student. It is 1 per student. Okay, so it's different. Why? Because the residential school, the students are spending the whole day in the school. So they are living their time and they are using water the whole day. Okay, but for the day school, only 5 hours, 6 hours they spend at school. They might use water. After that, there is no water usage. Okay, and it depends on the number of students. The more students, the more water usage. So it makes sense we use the number of students. Okay. For hospitals, it depends on the number of beds, because the more beds in the hospital, the more water usage. Okay? So we calculate as 4 PE per bed. Per bed is 4 PE. So if we have one hospital with 100 beds, so the PE of that hospital is 400. Okay? And for the hotels, it's same, but we use it per room, not per area or per story. No, it's per room. How many rooms in the hospital? For each room, we calculate 4 PE. Calculate as 4 PE. Okay? For the factories, it is calculated per staff. Per staff. So one staff is 0.3 PE. So if the factory has like 100 staff, okay, so the PE is 0.3 times 100. So it would be 30. Okay, so in that case we can add the consumption of I can add the consumption of factory. Let me put it in genre. Then for the mosque or masjid, it is 0.5 per person. Okay, if the masjid can occupy like 500, 1,000, three times 0.5. Then it goes to the temples. All other temples is 0.2, 0.2 PE per person. Okay, and this is the table that shows the whole type of premises or establishments that can use water. Okay, we have the residential, we have the commercial, and educational institutions, we have hospitals, hotels, factories. Okay, we have the market, if the wet market or dry market. We have the petrol station. It is per service bay. Okay, how many service bay? For the market, it is per stall. How many stalls? For the bus terminal, it is how many bus bay. For the taxi terminal, is how many taxi bay. Okay, and so on. For so for each premise, the PE is calculated depending on the water activity in that premise. And at the end, we will have for one city or one community or one district, we can calculate or estimate how much PE, which means that the water usage there equivalent to how many people. Okay? Equivalent to how many people. We have so many types of premises, but the actual usage is equivalent to how many people. Okay? That is the exact meaning of PE. Okay? So if you understand that, we move to the other part of the chapter, which is how to estimate the flow rate of wastewater. Now, during the day, the flow rate is fluctuating, as you can see. Okay, this is at midnight, 12 midnight. There is low consumption, and at 6 a.m., 7 a.m., people start waking up, going to their work, and preparing themselves to go to hospitals. Sorry, to schools, to university, to office. Okay, so the water usage becomes very high. Becomes very high. During the day, it's still high. Then after 7, 8 a.m., 9 a.m., 10 a.m., then until reach 12 a.m. Again. Okay, so that is also that the water usage will become lower, and then we'll continue the cycle. Okay, so it is vary hourly, daily, and weekly. Okay, so the peak flow occurs at maximum flow for the day. So this is the peak flow. This is a peak flow. We have like here our peak flow, and we have the average. We have the average. So in the design process, we have to consider both the average and the peak. Okay, so that's why sometimes we have to calculate both of them, right? We have to calculate the average the whole day. What is the average production and what is the peak? Because in the design process, we have to consider both. We have to consider the average, we have to consider the peak. We have to know that at a certain time, the peak will be 3 times the average. Okay? Or maybe 4 times the average. It depends. So that brings us to a point that we have something called the design flow rate, which is how many liter per capita per day should we consider? How many liters per capita, per person, I mean, per day should we consider for our design process? This is 225 liter per capita per day. This is the design flow rate. Okay, so one person is estimated to consume 225 liters per day. If we have 10,000 persons, so we just multiply together, we will have the average of the 10,000 persons, 10,000 population. Okay, but we have hotels, we have hospitals, we have schools, we have university, we have commercial buildings, we have houses. So how are we going to join all of this together? We calculate what? We calculate the PE. So the PE will represent the population number of people. Okay? Represent the population number. So if we know the population number represented by PE, multiply by design flow rate, so it will give us the average daily flow. Average daily flow. Average daily flow equals design flow rate times the PE. Design flow rate times PE. Okay, so this is the average daily flow. Okay, now this is the average. So how are we going to calculate the peak? Okay, the peak, there is a factor between the average and peak. What is this factor? It's called the peak flow factor. Okay, it's PFF. PFF equals 4.7 times P to the power minus 0.11. Okay, you remember that this P is the PE, but PE in thousands, which means that if PE is 20,000, so PFF equals 4.7 times 20 to the power minus 0.11. Let me write it here. If PE, for example, if PE equals 30,000, okay, so PFF equals 4.7 times 30, because we have to take the PE in 1000, 30 to the power minus 30 to the power minus 0.11. Okay, so this is how we calculate the factor. After we calculate the factor, we can calculate the peak flow rate. Okay, PFF times average daily. PFF times the average daily flow. Okay, so this is what we have to know about the estimations of flow. We just go for a simple example. Okay, this example, we have four types of premises in an example of a city. We have residential houses, we have 3,200 units. We have commercial building with a area of 10,000 meters square, primary school with 800 students. We have a private hospital with 120 beds. Okay, how much the daily flow average and how much is the peak? So first we have to calculate the PE. We have to calculate the PE. Okay, so according to each of premise, we can calculate the PE. For example, for the house, we have 3,200 units. Okay, and so the PE is 3,200 times 5 equals 16,000. Okay, for the commercial building, it's 10,000 meters square, so 10,000 times 0.3 over 100. Okay, the primary school is considered as day school here, so it is 800 times 0.2. Okay, for private hospital we have 120 beds, so that the PE is 120 times 4. Then we can add them together now, and we can get the total PE. Okay, the total PE is 16,940. Okay, so this is the total PE. After we get the total PE, we can calculate the average daily flow, the peak flow factor, and the peak flow rate. So the average daily flow is equal what? The the PE times the design flow rate. Okay, design flow rate times the PE. It gives us the average daily flow, and then we calculate the peak flow factor. Okay, this will gives us the ability to calculate the peak flow rate. Peak flow factor equals 4.7 times PE in thousand. You can see here this is the PE and this is the PE in thousands to the power minus 0.11. Okay, the peak flow factor is 3.445. So the peak flow rate is PFF times average daily flow. Okay, and will give us the final answer, which is 131. Okay, so that's all what we have, or that's all what we have for chapter 4. Okay, we have finished chapter 4 now, and I will post a group of questions for you, okay, for your revision and for your practice for chapter 2, 3, and 4, and mainly for chapter 3 and 4. Okay, and until this class, test 1 is covered. Okay, test 1 covers until this class. The classes after that is not covered in test 1, it will be covered in other tests. Okay, so I hope all of you have understood this class. There is no problem. If you have any question, regarding what we have discussed today, regarding anything we discussed today, if you have any question, I will be happy to answer. We can stop sharing. Test 1. What is test 1? Yeah, that's an interesting question. Test 1. This one is the midterm test. Okay, we have test 1, we have test 2, and we have the final test. Okay, there has to be 2 tests during the semester. You know that. Okay, we have presented this in the first class. The first class I recorded to you, and we presented that we have test 1 and test 2. Right? Am I right or wrong? Okay. I hope you are not shocked. But we have a test 1, but it's I don't know when, but at least you have 5 days or 1 week before test 1. But we still didn't have decided when the test 1 will be conducted. So test 1 include all calculation that we have learned from chapter 2, right? Yes, starting chapter 2, chapter 3, chapter 4. All the theoretical information and all the calculation questions. I mean calculation practice. Okay, so you have in the test you will have two parts. You'll have a theoretical part. And you have a practical part. I mean calculation part. Okay, the theoretical part covers like 10 to 12 marks, and the calculation part covers like 18 to 20 marks. It's something like that. Okay, so the total will be 30 marks, right? So this is until this class is covered on for this one. All right. Okay. So I hope all of you is happy to hear that there will be a test, but to do the test in all the tests, not only test 1. and all your course. Okay, for now we can end our class. If you don't have any question, if you have a question, just post it in the chat, or if you want to post later on the group, you can also post in the group of WhatsApp. Okay, so for now, thank you. Thanks to all of you for attending today, and wish to see you every time with these happy and smiling faces. And take care. Have a nice day. See you later. And